Okay, so this is the third video in the series of videos on system calls. And in this video, we are going to look at the actual system call implementation in Xv6. So if you've not seen part 1 and part 2 before, I recommend that you see those videos first. They give you a sort of overview of what a system call is and the how the architecture of the system call mechanism looks like. And then finally over here, we are going to see the actual code inside Xv6. So if you recollect, when I was talking about system calls before, I mentioned something about the IDT, the interrupt descriptor table. And I said that the IDT is something that is going to be initialized by the kernel when the kernel boots. So, you have, when you boot your system, you have the bootloader that starts, and then it transfers the context to the Xv6 kernel, and then the Xv6 kernel will start running, and then it will initialize a bunch of things. It will initialize this IDT as one of those things, and then it will start the other processors. So before we talk about system calls, let's look at how this IDT looks. That will help you in visualizing this abstract, thing called IDT. So there is a function that gets called during the boot flow. It's called tvinit. Now this PDF is just what I got from the MIT's Xv6 website. You search for MIT Xv6 and they have a link to the latest Xv6 sources. Over there they have a link to this PDF that is revision 10. And I like to use this PDF because they have this line numbers and it's easier to just go through the code here along with the line numbers. So we know we are talking about exactly the same thing. So on line 1 to 29, so on line 1 to 17, you see the function main. This is the main entry point for the Xv6 kernel. So when the bootloader transfers the context, execution context to the kernel, this is where it will start executing from. And if you look at this sequence where it initializes a bunch of stuff, and then it calls this 1233 start others, this function, this starts the other processors. So on a multi-processor system, you have one processor that's your BSP, which is called the boot system processor. And typically, even Windows and Linux operating systems boot like this. They boot on one processor, they do a bunch of initialization, and then they start other processors. And then part of the boot flow happens on multiple processors. So this video is not meant to be like it's not meant to talk about the boot flow because we are going to talk about system calls. So without going into a lot of details, let's just look at tvinit. This is defined on line 3367, and if you see here, it has this loop that goes from 0 to 256, and it calls this function setGate, which has a bunch of arguments. The first takes like an index into this structure called IDT. It's a global because it's clearly not defined here. It's actually defined on line 3367, just above it. So here is where your IDT is defined. It's basically just an array of struct gate descriptor. Don't need to worry about what a gate descriptor struct looks like. High level, you can just think of it as an array, and it has a bunch of things inside it. Let's look at the code for setGate. So over here, if you notice, it calls this setGate for all the vectors, and then it calls this setGate again for IDT t underscore syscall, and the interesting parameters that it passes are the last and the second last, these vectors and the DPL user. So let's look at this setGate, see what this expects. Defined on 0921, and if you look at the last argument, says descriptor privilege level, and it says the privilege level required for software to invoke this interrupt explicitly using an int instruction. So I mentioned that you can execute int64 from user space because that's the mechanism that system calls use, but you cannot execute any other int from user space because you have something like permissions in the IDT that tell you whether you can execute this int from kernel mode or user space. So this last field here is what tells that. If you look at this second last off is the offset, and basically this just means what function to execute when you get this particular interrupt. So let's go back to TV init and let's see how this t underscore syscall is defined. I've not looked at this revision 10 in a long time. Hopefully it should still be 64. Yes, line 3226, it is defined as 64, uh, which is your system call interrupt int64. And then if you look at DPL user, this should be defined as 3, because this tells you that you can execute int64 from privilege level 3. Here it is on line 0779. So the final thing inside gate, which is interesting, is this vectors t and sources call. So this, you can think of this as indexing into an array called vectors and then executing the function pointer at that particular array. So whenever you get like int 2, it will execute vectors 2 and index into vectors 2 and then execute the function defined there. If you get int 64, it will index into vectors using 64 and then execute the function that's defined there. The way these vectors, the different functions inside these vectors are defined is through a Perl script. So if you just search for vectors, again, I don't want to go into a lot of details here, but here is where it defines it. And if you look at line 3261, it has this ASM routine called dot global, and this dot global is just a way for you to define a function. So in C you just have a function, you just write the name and you define it that way. You can do the same thing in assembly using dot global, and that just defines a name, and then you can define what this, if this is a function, then you just define it as the function name and then colon, then the actual instructions that should be executed as part of these functions. So here it does this push li, and then it does this jump all traps line 3267. So in the previous video I mentioned something about the trap number that is pushed. So if you recollect, when you get an interrupt, the hardware is going to do certain things. It's going to switch to the kernel stack. It's going to push some of the states on the kernel stack. Then it is going to execute the function that's pointed to by the descriptor, which is this particular function. And now this function is going to push the interrupt number that was called, and then it is going to jump to this routine all traps. So for different interrupt vectors, it just pushes this different interrupt numbers, but then eventually all vectors just go to all traps. So all traps is where, which is what the entry point for all interrupts in Xv6 is. Before we look at what all traps is doing, let's look at the user mode code. The function printf and how it eventually ends up calling the int64. So the PDF that we were looking at before just has the kernel mode stuff, and if you just clone the latest Xv6 repo, you will get all the files, and there's certain files that have the user space libraries and the test applications and all those things. So let's just search for printf, and we are trying to, so this is where printf is called, similar to how you call in user space. And if you notice here, you have two arguments. First is an int and then the string. By default, printf just prints things to your screen, but the way it works in Xv6 is you always specify this first argument. So you can use printf to print stuff to a file as well. So if you want to print it to a screen, you just pass 0, and if you want to print your string to a file, you just pass the file handle. Let's look at how printf is actually defined. So over here, is where it is defined, and we can see there is some call called print int. Let's see what print int is doing. Actually, print int is just above it, and then we can see that it calls put c. So let's see that what this put c is. Aha, this looks like a system call. So write is a very common system call that you find in on all operating systems. You have open, close, read, write, so on. So let's look at how this write is defined. So in the file user.h is where the prototype is declared. It returns an int and it takes 3 arguments. And in uses.s is where all the system calls are actually defined. So they use this hash define, and then whenever these guys are going to be executed, they just end up calling this hash define, and the compiler just generates the functions this way, because this hash define basically has this it takes this name, whatever you are passing here, and then it does a dot global on that name, so it defines this name, and then it declares a function label using that name, and these are the two instructions that it does. So it does this move sys underscore name into EAX. So the convention here for Xv6 here in this code is, this is the source and this is the destination. So EAX is the destination, and then eventually it calls this int t underscore syscall, and we just saw that t underscore syscall is actually 64. So here is where it calls int 64. Let's see how this sys underscore name, different system calls are defined. So basically you just take this whatever is passed in syscall and just replace the name with whatever is passed. So for write, this will generate a global function write, and then the definition of write will be move sys underscore write to EAX. So let's see how sys score write is defined. Should be in syscall.h, and clearly this is just a number. And if you recall, we have two things. We have the interrupt vector, which you use as an index in the IDT, and then you have the system call number, which you use as an index to go to the system call table from which you execute the actual function. So here is where your system call numbers are defined. Come back on uses.s. So after it, so over here it will put 16 into EAX, and then it will call this syscall. If you recollect, in the previous video I mentioned that it uses EAX to store the syscall number, and then it calls this int syscall, which basically does all those things with the hardware doing a bunch of stuff, and then eventually jumping to all traps in Xv6. So let's look at what all traps is actually doing. Defined on 3304, and it's an assembly routine. Well, if you are reading assembly for the first time, this may seem overwhelming, but instead of understanding everything, just try to get a sense of things on the high level. But you'll see a lot of assembly routines inside any kernel, So if you're working on systems level, you sort of get familiar with reading assembly and writing assembly after a while. So basically this just pushes a bunch of registers on the trap frame. Before it does this, the hardware has already pushed certain states on the kernel stack, the ESP, the SS, ESP, CS, EIP, E flags. And then you have the vectors, function point, the vector index, the function pointed to by the vector index, which was pushing the interrupt number on the kernel stack. In this case, it will be 64, which eventually becomes a trap number. And then it jumps to all traps, which is going to push more general purpose registers on the kernel stack. and on line 3318 is where it does this push ESP. So if you remember, I mentioned it does this neat trick where it passes where it pushes the address of the ESP on the kernel stack and then calls this trap, so that this guy becomes an argument when trap is called. You should be very familiar with this sequence if you have done assignment 1. This is exactly how a function call works. You have, you push the argument, you call it, and then you clear the argument. So let's look at what trap is doing. Uh, okay, I have 85 hits when I type trap. So clearly we need to do something better, because we are not going to find it this way. Oh, actually we found something else. So if you look at line 0602, this is where your struct trap frame is defined. Okay, let me show you what trap looks like so you know what this trap frame is used for. Line 3401, trap is defined here, and the argument is, as expected, it is a struct trap frame pointer, and this trap frame is defined in this manner. And if you look at this order, this is exactly the reverse order in which things were pushed on the stack. The stack grows from high to low. Memory is always accessed from low to high. So these things, SS, ESP, E flags, EIP, error, were pushed by the hardware. This guy was pushed by line 0622 was pushed by your vectors function call, and then the rest of the things were pushed by all traps. And this trap frame is defined in the reverse order of the things that were pushed, so that because you passed the ESP itself on the kernel stack before you called trap, you can that becomes your pointer to this trap, and that points to EDI. So if you just do TF of EDI, ESI, EBP, you just access things on the kernel stack. If this doesn't make sense, go back to video number 2 and then come back here and read the code again, and hopefully that should make sense, or at least give you a better idea than before. So the first thing that this trap routine is doing is it checks if the trap number that was pushed on the trap frame is syscall. In this case, it will be a syscall because we'll be pushing 64 when you call int 64. And then it calls this function syscall. Let's see what this syscall is doing. Should be defined somewhere. And hopefully we'll find it real soon. Oh yeah, here it is. So 3701 is where syscall is defined, and line 3708, so on line 3706 it first reads the EAX member of the trap frame into this local variable num. Recall that we passed the system call number in EAX before we did int 64, and that EAX was pushed on the trap frame by all traps, and that's the reason you have the system call number here, which you are reading it into this variable num, and then you call this you take the num index into the syscall table and then call whatever function is defined at that index in the system call table. So the system call table is going to be an array, and every index in this array will have a function pointer. Actually, it's defined right here, line 3672. These are just the numbers, the index, and this is the function pointer at that index. So for write, it's going to be How come I can't find? Yeah, 3688. So instead of looking at sys write, let's look at uptime. You know, the all the system calls are implemented. The mechanism for all the system calls is the same. The actual implementation will vary from the system from one to the other. Write is going to be a little complicated. So instead of that, we'll look at uptime. And imagine instead of calling write, you had called uptime in your user space application. So only change will be instead of moving 16 into EX, it will move 14. It will do all those things which it did before. Now, if you look at uptime, and the reason I want to go over uptime is because in your assignment to implement a system call, you'll be implementing a system call similar to uptime. So let's look at what sys uptime is doing. It's defined on 3838. Basically, it just acquires lock, reads some global ticks, and then returns whatever it had read after releasing the lock. So come back to syscall here. Was it here? Oh, let's just use this twice. Yeah, here. So if you see here, whatever this function returned, it stores back into the EX member of the trap frame. So it uses this TF of EX for two things. When it enters, this is called TF of EAX has the system call number using which it indexes into the system call table. And when the system call is executed, whatever it returns is again stored into TF of EAX. The reason for this is when you go back to the user space from the kernel space, you pop all these registers into you pop all these members on the trap frame into the actual registers, and you'll be popping this TA of EAX into the actual EAX register, and that will have the return value when this int64 returns to the user space. And this is how a function also works in C, that whenever you call a function, if the function returns something, that's returned into EAX for x86. That's the reason you are storing this return value into EAX over here. So syscall will simply return back to trap. And let's see if trap is doing something more. Nope, it just returns. So you come back to all traps, and then it clears the argument that it had pushed. This is again the callee caller convention function call, and then it pops whatever it had pushed before. And then over here is where it calls the iret, executes the iret, right? So I mentioned, so if you want to return from a function in user space, you have the ret. If you are returning from an interrupt, you have the iret. The difference is the iret is going to pop all the states that was pushed by the hardware as part of entering this, as part of executing that int instruction. So it had, stored the ESP, CS, EIP, E flags. All those things will be popped back into the actual registers by this iret, and eventually, and this is how you end up going back to the user space right after int64 was called. So again, we saw how this code is implemented in Xv6 from the point where you have this system call in user space, how that translates into this int64 instruction, and then what is the entry point inside Xv6. Int64 is the hardware is going to switch to the kernel stack, save the state, call the vector function pointer. The vector function pointer is going to push the interrupt number on the stack, which is the kernel stack right now, and then it's going to jump to all traps. All trap is going to build the trap frame further and then push the ESP on the kernel stack itself before it calls its trap. trap has an argument of trap flame pointer. So it gets the address of the ESP, uses that as an argument, and it can access the stuff that all traps had pushed. Traps calls syscall, which takes the TF of EAX to index into the syscall table. The system call is eventually called. Whatever it does, it just stores it back in the TF of EAX, and then you simply return from this path and go back to the user space. So hopefully this should give you an idea of, these all three parts together should give you an idea of what a system call is, the basic mechanism of how a system call is implemented, and the actual implementation in Xv6. So if you have not read chapter 3 from the Xv6 textbook, I highly recommend that you read that chapter. It's very useful. And if you have any questions, you can post comments on this video here, or you can post questions on Piazza.